Welding is one of the most common processes in manufacturing industries. Most fusion welding processes have, however, a number of typical drawbacks. They require shielding gas and consumable materials, and produce intensive light, spatter, and fumes. Friction stir welding is a revolutionary process that avoids all these drawbacks. It is a clean, green, and safe process that joins metals by frictional heat generated by a rotating tool. It is a solid-state joining process, which means that the material is plasticized, but it never melts. This significantly decreases deformation and welding defects. The heat is generated through the friction between the tool and the material and through material deformation. This requires a significant downforce and a solid backing. With friction stir welding, it is also possible to join different types of materials, such as aluminium and magnesium. A friction stir weld is characterized by the circular pattern on the surface and the keyhole in the end. The Styrolite research project was started in 2009 at University West in collaboration with several industrial partners, both end users and process suppliers. The project aims to implement robotic FSW in Swedish transportation industries. Our welding lab at the Production Technology Center is equipped with a friction stir welding robot with embedded force control. The research is focused on automation and robotization of the process. Industrial robots with serial kinematics were not initially designed to perform heavy-duty operations. Typical robot operations are carrying welding equipment or pick-and-place operations of light components. For the friction stir welding process, however, the robot has to be much more powerful. These high forces will cause the compliant robot to deflect. One part of our research has been to find out the limitations of the robot system and to compare different path compensation strategies in order to decrease path deviations and improve the weld quality. The robot's capability of welding 3D surfaces is demonstrated through joining of complex car body parts. Knowledge from this demonstrator is fed back to designers to facilitate the future friction stir welded components. Another demonstrator shows the capabilities of welding steel and nickel-based alloys by robot. These materials require much higher temperature and process forces than aluminium, which puts more demands on the robot. Friction stir welding for straight joints is already widely adopted in the aerospace, marine, and railway industries. Recently, several automotive manufacturers have adopted the technology for straight-line geometries. Further development of FSW robots and process automation will facilitate for welding different materials in complex joint geometries in a fully automated production line. This contributes to the implementation of sustainable manufacturing processes and lighter vehicle constructions.